Hey guys, I thought it's time again for a new tutorial. Since it is currently very cold here and also my dive buddy is out and also not everyone has a dry suit, the diving opportunities are currently a little bit low, but that will change again soon, no worries. Nevertheless, I thought I'd create a new tutorial on the subject of diving and have picked out the topic of light refraction, and that has something to do with the question of why underwater everything is bigger or closer. So, first of all, I did a little experiment that maybe some of you know from physics class. All you need is a glass with water, preferable transparent, and a pen, a ruler, preferable something long and thin. And if you hold it in the water, it looks a bit closer underwater, and the pen looks a bit bent, which is difficult to show in the picture because you have to look at it from the side. But when I take the pen out again, the pen is completely straight, the same size, and not bent. And that is due to the light refraction. To take a closer look at the topic now, I have to clarify one small point at the beginning. Sometimes you hear that everything is bigger and closer underwater. Bigger and closer is not true. It is a bigger or closer. I read this again in the Encyclopedia of Recreational Diving from Paddy. The source is given here. So I'm diving in Egypt again and I see this fish in front of me. You know the picture? And either I perceive the fish now while diving bigger than it actually is or closer. This depends a little bit on how your brain works, and I don't want to go into it now. That would go a bit beyond the scope. We are now dealing with the physical effect of why the fish is bigger or closer. And now I have an abstract example of how light refraction occurs. Imagine you're driving your car into a curve and everything is normal, no black ice and nothing. And then you can also take the curve normally if you continue to steer. But if you're driving over a patch of ice like black ice and you're going a little too fast, then you might slip and in the worst case you might run out of the road. I hope that doesn't happen to any of you, but I think this is a very clear example that explains quite well what happened when you drive from one medium, I'm just going to skip to the next slide, over another medium. On the normal road, that means on asphalt or something else, you have a much firmer grip. That means your tires adhere quite well to the ground, and this suddenly no longer happens when you drive over the ice and then you slide to the side. And this is exactly what happened with light. When the light passes from one medium into another medium, and these media have different optical densities. Just accept the term of optical density now. It is a characteristic of each medium and it describes how fast the light can propagate in it. So in air the light can spread faster than in water. You all know that when you try to run in a swimming pool, you have much more resistance underwater than in the air. This is more difficult for you, and exactly the same happens with light. And then happens what I have to try to illustrate with the car, that the light is deflected. You can imagine it in such a way that the light slips or is slowed down, and if you are then in a curve movement, you can no longer follow the curve ideally. And here we simply remember, if we move from an optically thinner medium into an optically denser medium, then this angle of incidence becomes smaller. We say it is refracted towards the perpendicular. And if we observe the whole thing reversed, that means we move from an optically denser medium into an optically thinner one, from water into air for example, then this angle of refraction is a bit larger. So Now let's take a quick look at the mathematical description. If you are not interested in that, you can simply skip ahead 2 slides and then I will show you a small calculation example. So, the formula for this is the sinus of the angle of incidence alpha divided by the sinus of the refracted angle beta, and this behaves in the same way as the speed of light in the first medium divided by the speed of light in the second medium, here c1 and c2. These are material constants that you can read from any table. You don't have to determine them yourself every time. For the most common media, you can find them on the internet or in various tables or books. For our example here, from air to water, it would be the sinus alpha, the angle of incidence, divided by the sinus beta, the fractional angle, is equal to the speed of light in the air divided by the speed of light in the water. For those who want to know exactly, here is a small slide of explanation. So what exactly is sinus alpha and sinus beta? This is not necessary for the basic understanding. I just put it into the sake of completeness. For the inquisitive among you, alpha and beta, I have already mentioned, are the angles and they are generally designated with Greek letters. The sin or sine or sinus, as I have called it, is a so-called angle function, which is used among other things in the calculation of triangles for their angles and length. Who would like to know there now more, I refer to middle school mathematics books. There I do not go in more detail on it now. Let's take a look at another nice example. And we have this fish again. I have now simply assumed a few values and that the fish is now 10 centimeters high, so 5 centimeter up and 5 centimeter down from a center line and 1 meter away. Then, to calculate with the angle function, the angle from the upper edge to my eye is 2.86 degrees. And if you look at this again with the graphic here, there is now first of all the first simplification to see, so we go directly from the water into the air, which is in the mask, if it's hopefully not flooded. That means the light hits my mask at an angle of 2.86 degrees here, is then refracted. We have here the case optically dense to optically thin. That is the angle beta is slightly larger than 2.86 degrees. I have packed also again the light velocities in the media air and water on it. These are once 300 million meter per second in the air and once 225 million meter per second in the water. Let's put all this into the formula in the next slide. So sinus of alpha by sinus of beta is C water by C air. You can convert that. I have put this in detail on the next slide for those who want to calculate it. So we come to an angle of 3.815 degrees under which the light falls on your eye, though a larger angle than the incident 2.86 degrees. And as mentioned at the beginning, there are now two possibilities, namely that the hole is now perceived bigger or closer. Possibility 1, the fish is perceived bigger. Let's have a look at the whole thing again. At your eye, we have an incoming angle of 3.85 degrees. And if we now apply the angle functions to the actual distance of 1 meter, this is 6.668 centimeters upwards and downwards instead of the actual 5 centimeters. That means we experience an enlarged representation of the fish of 13.336 centimeters. So 33.36% bigger. And this is also very close to the textbook value that you might know, namely that you perceive things underwater 33% bigger. Of course, it is still a bit affected by rounding errors, and I have made another simplification which I will talk about at the end, but in a first approximation it fits quite well. We now first look at the second possibility, namely that the object is perceived closer. The light now continues to fall on our eye at an angle of 3.815 degrees. But now our brain does not think that the fish is bigger. The fish remains 10 centimeters. That is 2 times 5 centimeters. But the brain thinks it is now a few centimeters closer. And if we now say the previously calculated size of 13.336 centimeters related to a meter distance and now calculate down how close then the fish is if he is only 10 centimeters big. Though how close are these 10 centimeters are then? With a little percentage calculation we come to a distance of 0.7498 meters, so 0.252 meters closer. And because 1 meter is such a nice number, then this is equivalent to the percentage by which the hole is closer, namely 25.02% closer. So the reality now looks a bit more complicated. I have already mentioned here that I have made a small simplification. I'll go over it pretty quickly now. We have in the reality, of course, 3 media. Outside the water, then the glass of the mask, and then the air in the mask. You can see the speed of light in the glass also here. That are the 160 million meters per second. We now have 2 refractions and then make such a chain. That means we carry out the calculation from before again. Thus we got a second refracted angle, here gamma in addition. With numerical values it looks like this. At the beginning everything remains the same. We only change the speed of light in the class. We get a value sinus beta, which we don't have to solve it now. We can use it directly in the second step. This time between sinus beta and sinus gamma. Thus, from class to air, there results again an angle of 3.815 degrees. So rounded to 3 decimal places, the value is identically to the value determined before. And for the scope in which we have operated here, this is perfectly fine. If you look at more decimal places, it will of course deviate a bit, but we are not interested in that anymore. I hope you had some fun with this tutorial today, despite all the mathematics, and that you've learned something out of it. As always, I would appreciate your positive and especially your negative feedback. And if you're interested in any topic that you want me to do a tutorial on it, just put it in the comments and write me a DM or something else. I would be very happy. And until next time, and as always, good air.